الله الرحمن الرحيم. أبناء طلاب الفرقة الرابعة شعبة الرياضيات برنامج اللغة الإنجليزية. نبدأ اليوم محاضرتنا المقرر النظرية النسبية الخاصة Applied Mathematics 12. We now discuss some concepts. The first concept is reference frame. Physical phenomena are events that occur at a specific location and time. In order to measure these events and formulate the laws that govern them, we need an accurate hour to know the time of their occurrence, and space engineering that enables us to determine their location and the distance between these events. In mathematical model, the event is represented by geometrical point whose location is determined by measuring its coordinates from three plans called the basic plans. The main set of axes x, y, z, in addition to the clock, is known as reference frame, and this reference frame is denoted by the symbol S, where spatial coordinates are x, y, z, and time is t, and this is shown in figure 1. The observer who make the observations and measurements in this frame is symbolized by the symbol A. There is an infinite number of suitable frames that are suitable for measuring physical phenomena. The second concept we discuss is Newton's laws of motion. Newton assumed the existence of an suitable frame or verifiable frame, and all phenomena can be expressed or can be measured with respect to this verifiable frame. And this verifiable frame is called the absolute frame. Newton formulated his three known laws regarding to the absolute frame. If we code for this frame S, then Newton's laws take the following formula. The first law of Newton: if the force F acting on a particle is null, if F vanishes, then it is moving at a regular velocity v0 in a straight line, i.e. if the force F equals 0, then the velocity of the particle v equals dr by dt equals v0, where r the position vector of the particle, t time is measured with respect to the absolute frame s. So the path of the particle is, by integrating equation 1, we get the path of the particle r equals r0 plus v0 t, where r0 is the position vector at t equals 0. Equation 2, this is the equation of a straight line in the vector form. The second law of Newton: if a force F acts on a particle of mass m, it moves with acceleration. The particle moves with acceleration a, and we get F equals ma equals m d2r by dt square. The path of the particle depends on the form of the force F, the form of this force, or the form of the law of the force F. And if substitute by F and integrating this equation, we get R, the path of the particle. The concept, the third law of Newton: every action has a reaction of equal magnitude and opposite to it in direction, i.e. if the force F12 is the force that body 1 acts on body 2, and F21 that force which body 2 acts on body 1 at the same moment, then the third law mathematically can be written as F12 equals minus F21. This law means that if the two bodies are far apart, then each of them is affected by the other at the same moment, meaning that the influence of the forces is instantaneously. The third concept is absolute time. Absolute time. From Newton's first law, we find that if the force acting on a particle vanishes, the particle's path measured with respect to the frame S is a straight line. If we consider another frame S dash moving at a uniform velocity v in a straight line with respect to the frame S, we find that the particle is moving with respect to S dash at regular velocity v dash, which is given by the formula v dash equals v minus v minus capital V, where v the velocity of the particle with respect to S, where v is the velocity of the particle with respect to S. If r dash is the vector of position of the particle with respect to the frame S dash, then equation 5 can be written as dr dash by dt dash equals v minus capital V, where t dash is the time with respect to S dash. And by substituting v from equation 1, v, this velocity equals v naught. Then equation 6 takes the form dr dash by dt dash equals v naught minus capital V, Vd equals v naught. By integrating equation 7 with respect to time t dash, then we find that r dash equals v naught salib v minus v t dash plus r dash naught, where r dash naught is the position of the particle at moment t dash equals 0. Equation 8 is the equation of the path of the particle if it is observed by the observer B in the frame S dash. And equation 8 is a straight line in the vector form. Now assuming that the two frames S dash apply when t dash equals 0, at this moment r dash naught equals r naught. From figure 2 we get the relation. From this figure we get the relation between the three vectors r dash vt. We get from this figure the relation r dash equals r minus vt, and r we can substitute from equation 2 in this equation. We get R dash equals V naught minus V divided by T plus R naught. By comparing equation 8 and equation 9, equation 8 and equation 9, we find that T equals T dash. The condition 10 means that the time is absolute and it does not depend on the frame measured in it. The time is absolute and does not depend on the frame measured in it. The principle of symmetry of observers and Galileo transformation. The physical phenomena that occur in the universe, in the space, are completely independent of the observer who observes them. If the observer A finds that the path of a particle is a straight line and deduces from this that the particle is not under the influence of a force, then the observer B, who moves at a uniform velocity, a straight line, with respect to the observer A, the observer B must find that as well. This is expressed that the observers in inertial frames are the same or are equivalent to describe physical phenomena. The relation between measurements of the observers in inertial frames can be found by transformations. Assume that the frame C dash moves with respect to the frame S at a regular velocity capital V in a straight line. We found previously that T dash equals T, and from figure 2 also we found R dash equals R minus Vt. T dash equals T and R dash equals R salib Vt. The two equation 11 are known as the Galileo transformation. The Galileo transformation. Under this transformation, which links the measurements of observers A or B each other, under this transformation, we find that Newton's second law preserves its form. So, if we assume that the form of this law, second law of Newton, if we assume that the form of this law in relation to the observer A is second law of Newton relative to A, m d2r by dt square equals f, and for what is observed B is relative to B, we can write d2 d2 r dash by dt dash by dt dash square equals d2 by dt t dash equals t dt d2 by dt square multiplied by r salib vt equals d2 r by dt square. And if we denote the measured force with respect to the observer B, symbolize f dash, then f dash equals m d2 r dash by dt dash square equals m d2 r by dt square equals f. And this means that the Newton's law are invariant in form under Galileo transformation. In equation 13, we write f dash equals m dash, which equal m, i.e. in equation 13 we put with Newton that m equals m dash. M equals m dash, that is the mass of a particle is absolute, i.e. not dependent on the frame measured with respect to it. And now we discuss this result. If we impose two events that are localized in relation to the frame S by R1 and R2 at the same time, then their location in relation to the frame S dash R R-1 equals R1 minus Vt, and R-2 equals R2 minus Vt, and subtracting these two relations, we get these two relations leads to R-1 minus R-2 square equals R1 minus R2 square. That is the distance between the two events remains invariant in the form under Galileo transformation. This means that the measured lengths are absolute. If we take the two events very close to each other, then relation 15 becomes the r dash square equals the r square. Or by using the components of these two element vector, we get dx dash square plus dy dash square plus dz dash square equals dx square dy square plus dz square. This form is called the square of the element of length in the Euclidean triple space, and is denoted by the symbol ds square, where ds is the element length. السلام عليكم ورحمة الله وبركاته.